Picture standing on a Roman harbour that's been pounded by Mediterranean storms for 2,000 years, yet its concrete foundations are actually stronger today than when they were first poured, while our modern concrete crumbles after just 50 years. So sit back, grab a cup of tea, and get ready to discover the remarkable story of Roman concrete that gets stronger underwater. Explore the volcanic ash secret that built harbours and aqueducts still standing today. Learn how ancient engineers created self-healing structures that repair their own cracks, and understand what Roman innovation can teach us about building for the future in ways modern science is only now beginning to comprehend. In the year 27 BCE, Roman engineers faced an impossible challenge. Emperor Augustus had ordered the construction of a new harbour at Caesarea Maritima on the eastern Mediterranean coast. The site offered no natural protection, waves crashed directly against the shore, and any normal construction material would be destroyed by the relentless sea. Yet within a decade, Roman builders had created massive concrete breakwaters that not only survived the pounding waves, but actually grew stronger from constant contact with seawater. This wasn't magic or divine intervention. It was the result of Roman engineers discovering and perfecting one of the most remarkable building materials in human history: hydraulic concrete made with volcanic ash. While modern Portland cement degrades in seawater, dissolving and weakening over time, Roman marine concrete has endured for 2 millennia and counting. Recent scientific analysis reveals why. The Roman mixture doesn't just resist the sea, it recruits seawater as an ally in an ongoing chemical reaction that strengthens the material over centuries. The secret ingredient came from the volcanic regions around the Bay of Naples, particularly near the town of Puteoli, modern Pozzuoli. Here, violent volcanic eruptions had deposited layers of ash that locals called pulvis puteolinus, which we now know as pozzolana. This wasn't ordinary ash, but a complex mixture of alumina and silica in an amorphous, glassy state that possessed almost magical properties when mixed with lime and seawater. The discovery of pozzolana's properties likely happened by accident, as many great innovations do. Perhaps a builder short on sand substituted volcanic ash in a mortar mixture, or coastal construction exposed lime ash mixtures to seawater. Whatever the origin, by the 1st century BCE, Roman builders had recognized that certain volcanic deposits created concrete with extraordinary properties. It hardened underwater, resisted erosion, and actually improved with age. Understanding why pozzolana works requires a brief chemistry lesson. When volcanic ash mixes with lime, calcium hydroxide, and water, it creates a pozzolanic reaction. The silica and alumina in the ash react with calcium hydroxide to form calcium silicate hydrate, CSH, and calcium aluminate hydrate, CaH compounds. These compounds bind aggregate materials together in a dense matrix far stronger and more durable than simple lime mortar. But seawater added another dimension to Roman concrete's chemistry. The chlorides and sulfates in seawater, which attack modern concrete, instead participated in beneficial reactions with Roman marine mixtures. Seawater's magnesium and sulfate ions reacted with the lime and volcanic ash to create new binding minerals. Most remarkably, these reactions continued for centuries, with seawater percolating through the concrete and generating new crystals that filled pores and cracks. The Romans didn't understand this chemistry in modern terms, but they understood the results. Through centuries of trial and error, they developed precise recipes for different applications. Vitruvius, the Roman architect and engineer, documented these recipes in his treatise De Architectura. For marine structures, he recommended a mixture of 1 part lime to 2 parts pozzolana. For buildings on land, the ratio changed to 1 part lime to 3 parts pozzolana or regular sand. These weren't arbitrary ratios, but the result of extensive experimentation. Too much lime and the concrete would crack as it cured. Too little, and it wouldn't achieve full strength. The quality of ingredients mattered enormously. Builders learned to identify the best volcanic ash by its color and texture. The finest pozzolana had a reddish hue and felt slightly greasy between the fingers. They discovered that certain quarries produced superior material and guarded these sources jealously. Lime production itself required considerable skill. Romans burned limestone in special kilns at temperatures exceeding 900 degrees Celsius, converting calcium carbonate to calcium oxide, quicklime. This process, called calcination, had to be carefully controlled. Underburned limestone wouldn't react properly. Overburned material became dead-burned and useless. Master lime burners commanded high wages for their expertise in judging when the transformation was complete. The mixing process proved equally critical. Romans discovered that hot mixing, adding quicklime directly to the volcanic ash and aggregate, produced superior results. The heat generated by quicklime reacting with water, slaking, may have initiated beneficial chemical reactions. Recent analysis of Roman concrete reveals another crucial factor. They deliberately included small chunks of unmixed lime throughout the mixture. These lime clasts, long thought to be defects, actually enable the concrete's self-healing properties. When cracks form in Roman concrete, they preferentially travel through these softer lime clasts rather than the harder binding matrix. This exposes unreacted lime to moisture, triggering new chemical reactions. The lime dissolves, flows into the crack, and then recrystallizes as calcium carbonate, effectively healing the damage. It's an engineered self-repair system that modern materials scientists are only now learning to replicate. The construction techniques for underwater placement showcased Roman engineering ingenuity. Building harbour moles and bridge foundations required pouring concrete into the sea itself. Romans developed several methods, each suited to different conditions. For shallow water they built temporary cofferdams, double-walled wooden enclosures, pumped dry to create a workspace. The concrete could then be placed in the dry, though it would eventually be submerged. For deeper water, cofferdams became impractical. Instead, Romans pioneered the use of floating forms and underwater placement. They built wooden forms on barges, filled them with concrete, then sank the entire assembly into position. The hydraulic properties of pozzolanic concrete meant it would harden properly even when placed directly in seawater. Some projects used a technique called tremi placement, lowering concrete through tubes to minimize mixing with water during placement. The scale of Roman marine construction projects still impresses engineers today. At Porcius, the artificial harbour serving Rome, builders created a harbour basin covering 200 hectares, protected by massive concrete moles. The lighthouse foundation alone required thousands of cubic meters of concrete. At Caesarea Maritima, King Herod's engineers, using Roman techniques, built breakwaters extending 500 meters into the sea, creating a harbour from nothing but concrete and determination. These harbours transformed Mediterranean trade. Ships could now shelter in artificial ports where nature provided no protection. Cities grew in previously impossible locations. The reliability of Roman harbours, knowing they would last generations without major repairs, encouraged long-term investment in port facilities. Warehouses, docks, and commercial districts developed around these permanent maritime infrastructures. But marine construction was only one application of Roman concrete. Aqueducts carrying fresh water across hundreds of kilometres relied on waterproof concrete channels and bridge piers that could withstand flooding. The Pont du Gard in southern France stands as perhaps the finest example. Its concrete and stone piers have supported 3 tiers of arches for 2,000 years, surviving floods that would demolish modern bridges. Urban construction showcased different concrete innovations. The Pantheon in Rome, completed around 126 CE, demonstrates Roman mastery of concrete in architecture. Its dome, still the world's largest unreinforced concrete dome, used a sophisticated gradation of aggregate. Heavy basalt at the base transitioned to lighter pumice near the top, reducing stresses while maintaining strength. The concrete mixture itself varied by location, optimized for each structural role. Roman builders also understood that different applications required different aggregates. For marine structures, they used volcanic tuff, a light, porous rock that bonded well with the cement paste. Buildings employed brick fragments and tile shards, which created strong bonds and added pozzolanic properties of their own. Decorative concrete might include marble chips for appearance. This tailoring of materials to purpose shows sophisticated understanding of composite material properties. The Romans developed specialized concretes for extreme conditions. In Bath, England, Roman engineers built pools and channels handling hot mineral springs. The concrete had to resist not just water, but high temperatures and aggressive chemical conditions. They succeeded by adjusting their standard recipes, creating material that survived conditions that destroy modern pool concrete. Analysis shows they used a higher proportion of lime and selected aggregates that remained stable at elevated temperatures. Foundation work in challenging soil conditions pushed Roman concrete technology further. Building in marshy ground around Rome required concrete that could cure in saturated soils while resisting settlement. Roman engineers developed techniques for ground improvement, using concrete, driving piles, and creating reinforced platforms that distributed loads across weak soils. Many Roman structures built on seemingly impossible sites remain stable today, while adjacent modern buildings require constant maintenance. The economic network supporting Roman concrete construction spanned the empire. Pozzolana from the Bay of Naples was shipped throughout the Mediterranean, carried as ballast in grain ships returning from Italy. Quality control mattered. Inferior volcanic ash could ruin an entire project. Merchants who adulterated pozzolana with regular sand faced severe penalties. Trade guilds developed certification systems with sealed containers guaranteeing authentic material from specific sources. Transportation logistics posed constant challenges. A major construction project might require thousands of tons of pozzolana, lime, and aggregate. Roman efficiency in moving bulk materials enabled projects inconceivable in earlier eras. Purpose-built ships carried construction materials along with specialized crews who understood proper storage and handling. Pozzolana had to stay dry during transport. Exposure to moisture started reactions that reduced its effectiveness. The social organization of Roman construction reveals a sophisticated industry. Specialized workers handled different aspects of concrete work. Lime burners operated kilns, often in families maintaining trade secrets across generations. Mixers understood proportions and techniques for different applications. Placers specialized in handling fresh concrete, understanding how long they had before initial set, and how to achieve proper consolidation. This specialization enabled consistent quality across vast projects. Training systems ensured knowledge transfer. Apprentices learned by observation and practice, gradually taking on more responsibility. Master builders jealously guarded certain secrets while sharing basic knowledge freely. This balance between proprietary knowledge and open education created innovation within tradition. Roman concrete recipes show gradual refinement over centuries rather than revolutionary changes, suggesting systematic improvement based on shared experience. The Roman approach to quality control seems remarkably modern. Major projects employed inspectors who checked materials and methods. Contracts specified concrete strengths and durability requirements with penalties for failure. Some contracts required builders to guarantee their work for specific periods. A bridge might carry a 40-year warranty. This accountability encouraged best practices and punished corner cutting. Record keeping, though fragmentary today, shows Romans documented their construction methods. Building inscriptions often recorded not just who commissioned and built structures, but technical details like concrete volumes placed. Administrative documents mentioned specific quarries for materials and even individual work crews. This documentation helped spread best practices across the empire while creating accountability chains that improved quality. The gradual decline of Roman concrete technology parallels the empire's fragmentation. As centralized authority weakened, the network supplying quality materials broke down. Local builders, cut off from traditional pozzolana sources, attempted substitutes that failed to match the original's properties. The specialized knowledge of proper proportions and techniques, maintained by urban guilds, dissipated as cities shrank and construction slowed. Medieval builders inherited Roman structures, but not the knowledge to replicate them. They marveled at ancient concrete's durability, while their own mortars crumbled within decades. Some attempted to recreate Roman concrete by crushing old Roman buildings and reusing the material, missing the point that the magic lay in the original ingredients and methods, not the finished product. This recycling destroyed many Roman structures while failing to capture their essence. The Renaissance brought renewed interest in Roman construction methods. Architects studied Vitruvius and examined surviving structures. Yet despite access to the same volcanic ash sources, Renaissance builders couldn't match Roman concrete quality. They missed crucial details: the hot mixing process, the importance of seawater in marine applications, and the beneficial role of lime clasts. Their improved methods, based on incomplete understanding, actually produced inferior results. The development of Portland cement in the 19th century seemed to render Roman methods obsolete. Portland cement was stronger initially, more predictable, and could be manufactured anywhere from common limestone and clay. The construction industry embraced this new material enthusiastically, dismissing ancient methods as primitive. Only when early reinforced concrete structures began deteriorating, after mere decades, did engineers question whether newer automatically meant better. Modern analysis of Roman concrete began in earnest during the 1990s. Advanced techniques, electron microscopy, X-ray diffraction, and nuclear magnetic resonance revealed previously hidden details. Scientists discovered the ongoing chemical reactions, the role of seawater, and the self-healing mechanisms. Each discovery increased respect for Roman achievement, while highlighting modern concrete's limitations. Roman builders had solved problems we're still struggling with today. The environmental implications of Roman concrete have gained attention as climate change accelerates. Portland cement production generates approximately 8% of global CO2 emissions. Manufacturing requires heating limestone and clay to 1450 degrees Celsius, far higher than Roman lime kilns. Each ton of Portland cement releases nearly a ton of CO2. Roman concrete's lower processing temperatures and pozzolanic reactions that actually absorb CO2 over time make it far more climate-friendly. Durability multiplies environmental benefits. If Roman harbours last 2,000 years, while modern ports need reconstruction every 50 years, the ancient method requires 40 times less material over time. Reduced maintenance means less energy expenditure, fewer emissions from construction equipment, and less disruption to marine ecosystems. The Romans achieved sustainability through longevity rather than recyclability, a lesson worth considering in our throwaway age. Current research focuses on adapting Roman principles to modern needs. Scientists have successfully recreated self-healing concrete using similar lime-clast mechanisms. Others experiment with modern pozzolans, fly ash from coal plants and blast furnace slag, that provide similar chemical properties to volcanic ash. These efforts aim to capture Roman concrete's benefits, while maintaining modern construction's speed and predictability. Several pilot projects now use Roman-inspired concrete formulations. In Wales, researchers built a test seawall using hot-mixed lime concrete with volcanic ash. After 5 years, it shows increasing strength and no deterioration despite constant wave action. In Italy, restoration projects increasingly use authentic Roman formulations when repairing ancient structures, finding that matching materials provide better compatibility than modern substitutes. The biomimetic aspects of Roman concrete inspire materials scientists. Like bone or shell that grows stronger at stress points, Roman concrete responds to its environment by generating new mineral growth where needed. This adaptive behavior contrasts sharply with modern concrete's passive deterioration. Researchers now explore how to engineer materials that actively respond to environmental challenges rather than merely resisting them. The economic implications of adopting Roman techniques face modern construction industry realities. Portland cement's dominance stems partly from standardization. Engineers can specify exact strengths and predict behavior. Roman concrete's site-specific optimization and long-term strength gain complicate modern fast-track construction schedules. Projects designed for 30-year lifespans don't value 2,000-year durability. Changing this requires rethinking how we value infrastructure investment. Cultural attitudes toward time affect material choices. Romans built for eternity, expecting their descendants to use the same harbours and bridges centuries later. Modern societies optimize for initial cost and short-term performance. We finance infrastructure through 30-year bonds, not 300-year horizons. Roman concrete's advantages only manifest over timescales beyond quarterly earnings reports. Capturing these benefits requires institutional changes beyond mere technical improvements. Education about Roman concrete could shift perspectives. Engineering curricula typically present Portland cement as concrete's evolution, relegating Roman methods to historical footnotes. Yet Roman concrete offers profound lessons about working with natural materials, understanding environmental chemistry, and designing for longevity. Integrating these lessons throughout engineering education might produce designers who think in centuries rather than decades. Public awareness of Roman concrete usually focuses on mystery and lost secrets. Popular articles emphasize rediscovered ancient wisdom, feeding narratives about forgotten superiority. While Roman concrete was indeed remarkable, this framing obscures the real lesson. Patient observation and incremental improvement over centuries created exceptional results. The Romans didn't possess mystical knowledge, but rather commitment to long-term refinement. The aesthetic legacy of Roman concrete deserves recognition. Unlike modern concrete's uniform grey surfaces, Roman concrete displayed rich textures and colours from its varied aggregates. Exposed volcanic rock, brick fragments and marble chips created visual interest. Roman builders often left concrete exposed, rather than covering it, confident in its appearance. This integration of structure and surface offers lessons for contemporary architecture seeking to honestly express materials. Maintenance philosophies differed radically between Roman and modern practice. Romans expected structures to largely maintain themselves through self-healing mechanisms and inherent durability. When repairs were needed, they used compatible materials that integrated with original fabric. Modern maintenance often involves incompatible patches that create new problems. Roman structures teach that proper initial construction reduces lifetime maintenance far more than frequent repairs. The spiritual dimension of Roman construction, their belief that structures should honor gods and empire through permanence, motivated exceptional effort. While we can't replicate their religious motivations, we might consider what values could inspire similar commitment to quality. Perhaps building for climate resilience or intergenerational equity could provide modern equivalents to Roman civic pride. Technical knowledge alone doesn't create great architecture. Cultural values shape how we apply that knowledge. Archaeological discoveries continue revealing Roman concrete innovations. Recent underwater excavations found harbour structures with specialised concrete formulations for different depths. Shallow water installations use different mixtures than deep foundations, optimised for varying pressure and temperature conditions. This fine-tuning shows Romans understood their materials' behaviour in ways we're still discovering. Each excavation adds details to our understanding of their sophisticated practices. Climate science unexpectedly benefits from Roman concrete studies. Ancient structures provide climate records through their materials. Growth rates of minerals in Roman marine concrete indicate seawater temperatures during formation. Isotope ratios in lime reveal atmospheric conditions during manufacture. These structures serve as inadvertent climate observatories, their very substance recording environmental conditions across 2 millennia. Roman builders unknowingly created archives encoding their climate in stone. The search for modern pozzolans drives current research. While volcanic ash remains geographically limited, industrial byproducts offer alternatives. Fly ash from coal combustion contains similar aluminosilicate glasses. Ground granulated blast furnace slag provides comparable reactivity. Agricultural wastes like rice husk ash show promise. These materials transform industrial waste into valuable construction resources, echoing Roman efficiency in using available materials optimally. Nanotechnology offers new perspectives on Roman success. Analysis reveals that Roman concrete's strength comes partly from nanoscale crystal structures formed during pozzolanic reactions. These crystals, smaller than modern cement particles, create incredibly dense matrices resisting crack propagation. Understanding these nanostructures guides development of new materials, combining ancient chemistry with modern processing to achieve unprecedented properties. The Romans stumbled upon nanotechnology through patient empiricism. Computer modelling now simulates Roman concrete's long-term behaviour. These models predict how different formulations will perform over centuries, compressing millennia of experience into months of calculation. Virtual testing explores how Roman principles might apply to modern challenges like nuclear waste containment, where 1,000-year durability is essential. Digital archaeology thus becomes engineering futures, using ancient wisdom to solve tomorrow's problems. the philosophical implications of Roman concrete extend beyond materials science. Their success challenges progress narratives assuming steady technological improvement. In concrete technology, we arguably peaked 2,000 years ago and are only now recovering lost ground. This humbling realization questions other assumptions about modern superiority. What other ancient technologies might we profitably re-examine? Roman concrete proves old solutions can surpass new ones. International collaboration advances Roman concrete research. Italian volcanologists share ash samples with American materials scientists. British archaeologists coordinate with Japanese engineers studying earthquake resistance. This global effort mirrors Roman practices. Their empire succeeded by adapting local knowledge while maintaining standards. Modern research networks recreate ancient knowledge networks, proving certain organizational patterns transcend technology in enabling innovation. The construction industry slowly acknowledges Roman lessons. Forward-thinking firms experiment with Roman-inspired mixtures for specialized applications. Marine contractors particularly value self-healing properties for underwater structures. Some specify hot-mixed lime mortars for restoration projects. While wholesale adoption remains distant, niche applications prove viability. Markets for thousand-year concrete may be small, but growing as climate change highlights infrastructure vulnerability. Regulatory frameworks struggle with Roman concrete's characteristics. Building codes assume concrete reaches final strength within 28 days. Roman concrete strengthens for decades. Standards specify minimum cement content. Roman marine concrete performs better with less binder. Prescriptive regulations based on Portland cement properties actively prohibit optimal Roman formulations. Updating codes requires extensive testing and bureaucratic battles, slowing adoption despite proven performance. The economics of durability face accounting challenges. How do you value a bridge lasting 2,000 years versus one needing replacement every century? Discount rates make distant benefits worthless in present value calculations. Yet society clearly benefits from Roman infrastructure still serving after 2 millennia. New economic models incorporating intergenerational equity and option value might better capture long-term benefits. Roman builders lacked our mathematical tools, but intuited durability's true worth. As we near our conclusion, let's consider what Roman concrete teaches beyond materials science. First, patient observation and incremental improvement can achieve results that deliberate innovation might miss. Romans didn't set out to invent self-healing concrete, they discovered it through centuries of practice. Second, working with natural materials' inherent properties often surpasses forcing materials to meet predetermined specifications. Roman builders adapted to volcanic ash's characteristics rather than modifying it. Third, understanding comes from multiple perspectives. Romans succeeded through practical experience while lacking theoretical chemistry. Modern science explains their success theoretically, but struggles with practical implementation. Combining both approaches, respecting traditional knowledge while applying scientific analysis, offers the best path forward. Neither dismissing ancient wisdom nor uncritically accepting it serves progress. Fourth, sustainability through durability deserves reconsideration. Our recycling focus assumes short lifespans and repeated manufacturing. Roman concrete suggests building once for millennia might be environmentally superior. The most sustainable building is one that never needs replacement. This challenges design philosophies, prioritizing adaptability over permanence, but offers important alternatives for truly permanent needs like sea defenses. Fifth, institutional timescales shape technological choices. Romans built for empire expected to last forever. We build for corporations with quarterly horizons. Changing technology requires changing institutions valuing long-term thinking. Roman concrete's lessons extend to governance, finance, and social organization. Technical solutions alone cannot create sustainable infrastructure without supporting social structures. As you finish your tea and reflect on Roman concrete's remarkable story, consider how their patient perfection of volcanic ash mixtures might inspire modern approaches. Not every problem needs revolutionary solutions. Sometimes evolution through careful observation surpasses disruption. Not every material needs modification. Sometimes understanding and working with natural properties achieves better results. The Roman harbours, still standing after 2 millennia, pose a question we must answer. Will anything we build today survive as long? If not, what does that say about our technological progress? Perhaps true advancement means learning from our predecessors' successes rather than dismissing them as primitive. Roman concrete stands as solid proof that ancient wisdom, properly understood, can solve modern problems. The volcanic ash that Roman builders mixed with lime carried the geological power of Earth itself, the planet's fiery interior providing materials that could withstand its ocean's assault. In learning to work with these forces rather than against them, Romans achieved what we still struggle to match. Their concrete doesn't just resist nature, it enlists nature as an ally in an ongoing process of strengthening and self-repair. Today's engineers facing climate change, sea level rise and infrastructure decay would do well to study Roman harbours standing firm against millennia of storms. Not for slavish imitation, but for inspiration about working with natural processes, building for the long term, and achieving sustainability through durability. The Romans showed us the way. We need only the wisdom to follow their example, adapted to our times. In the end, Roman concrete reminds us that human ingenuity isn't always about inventing something new. Sometimes it's about perfecting something old, understanding something natural, or committing to something lasting. The Romans mixed volcanic ash with lime and created structures that outlasted their empire by 15 centuries and counting. What might we achieve with similar patience, observation, and respect for the materials our Earth provides?